Today we're talking about 3C, we're talking about stationary points. Oh, absolutely. Beautiful manners. So, this green box here is going to be pretty important. But what I want to do first is I just want to stress the point, because every year I always have people getting confused about f of x and f dash of x, okay? So what we were doing in the last lesson is f dash of x tells us the slope of f of x, okay? And we know if f of x looks something like this, okay, we can see where it's increasing and we can see where it's decreasing just by looking at it. Just like this graph I've got there, you can see that it's increasing until that local max at 0, and then decreasing to some x value, and then it starts increasing again. So you can see that just by looking at it. But what we're doing is we're using calculus methods to find when it's increasing and decreasing. F dash of x is the slope function. We're drawing the sine diagram of f dash of x. Alright, and if we draw the sine diagram of f dash of x, it's going to look like this. I'm going to draw it with its corresponding parts underneath. It's going to be increasing, and then decreasing, and then increasing. That this tells us, the sine diagram of f dash of x tells us when f of x is increasing and when f of x is decreasing. So don't get them confused, they're not the same function. We're using f dash of x to tell us about f of x. Now you may sketch the graph of f dash of x in order to get the sine diagram of f dash of x, but that sine diagram doesn't tell you when f dash of x is increasing, it tells you when this function is, okay? So just be aware of that. So we've got the green box there, we've got local min, local max, and their corresponding sine diagrams, what their sine diagram is going to look like. And then we have this new terminology, it was introduced to us last year, it's called a stationary point of inflection, which is a special case, and that's just when we have a sine diagram with either two positives either side of a root, or two negatives either side of a root, and that's going to pop up in one of our examples here. So let's get into the first example. We've got our process listed there. It says find f dash of x and draw its sine diagram. Hence find the y coordinate for the given stationary points, and hence find the state, the nature, and coordinates of the points. So this is our function, x to the power of 3. Take 3x squared, take 2. Simple differentiation. dy and dx is going to be 3x squared take 6x. And so when we're drawing a sine diagram, what we're doing is we're saying, what are the roots? What are the values that are going to make this equal to 0? What are its x-intercepts? And so if you can't see them, what you do is you make that statement. What's going to make 3x squared take 6x equal 0? We can factorise 3x, and then we can apply the null factor law. 3x is 0, or x take 2 is 0, and we've got our solutions. Okay, so I don't expect you to be able to see the answers there, all right? But that's what we're trying to find. We're trying to find the values for x for which it's equal to 0, the x-intercepts occur. So we've got 0, and we've got 2, okay? And then at this stage, like this is one thing we learned in year 11. We said you can make a mathematical argument to find the sine diagram, okay? So you could go, all right, when x is 1, okay, because x is a number that occurs between 0 and 2. If I go, when x is 1, and let's crunch that. When x is 1, y is going to be 3 times 1 squared, take 6 times 1. And I'm using this function because we're drawing the sine diagram of this function, okay? I understand that says y, this is dy and dx, but we're drawing the sine diagram of this function. So we're putting x is 1 in here. We're going to have 3 times 1 squared, take 6 times 1. That's 3 takes 6, we've got minus 3. Now the value is not significant, but the fact that it's negative, that's what we're looking for. Because it's a negative number between these 2 points, that means on our sine diagram it's going to be negative between those 2 points. That does not necessarily mean it's going to be positive either side here, okay, although it is in this circumstance. You can investigate further. What's a number that's less than 0? So when you put in x is minus 2 or minus 1 into the equation. What's a number that's greater than 2? So you put in x is 3. Okay, so that's how you can make a mathematical argument to come up with a sine diagram. Right? You identify the roots or any asymptotes, and then you just chuck x values either side of those, generate the sign diagram. The other way is, of course, just to graph that and look at the graph and say, when is it above, when is it below? All right? And so what that means, remember, this is the sign diagram of f dash of x. So this means, I'll rub this out so we're not looking at that. This means f of x is going to be increasing for values up to 0. And then between 0 and 2, it's going to be decreasing. And then for values greater than 2, it's going to be increasing. And we can see that mirrored up here. Okay, we can see it's increasing until we get to 0, then it's decreasing until we get to 2, and then it's increasing again. And you can even graph the original function and just g-solve those points. You can g-solve the max, tells you the coordinates, and you can g-solve the min as well. All right, so that's how we would use our graph to answer this. But again, we're applying those calculus methods. Okay, then we need the coordinates. We need to say, well, these are the coordinates of the stationary point, but what is the corresponding y value on the original function? Because we're asked the nature of the turning points on y. So we're going to go, when x is 0, what's the value of y? So when x is 0, y is going to be minus 2. Putting 0 in here, we're going to have 0, take 0, we're just left with minus 2. And when x is 2, we're going to have to do a bit of crunching here. We're going to have 2 to the power of 3. Take 3 times 2 squared, take 2. 8, take 3 fourths, 12, take 2. 8, take 14, minus 6. Alright, so we've got the coordinates. Okay, and we're ready to make our final answer. And I might make our final answer up here, so people aren't bending their heads. So this is what we're learning here today. So I expect perhaps everything we've just done is maybe what we were doing in increasing and decreasing. This is the part we're talking about. We can see from here it's increasing, it gets to x is 0, and then it starts decreasing. So it's going like this. Right, we've got a local max. Okay, so we're going to say local max at, and we've got the coordinates, x is 0, y is minus 2. And then we can see, then between 0 and 2, we're decreasing until it gets to 2, and then increasing, so we have a local min. And we've got x is 2, y is minus 6. Okay, that's what we're doing here. All right, so again, you can get this answer from your calculator, right? But it's about that process, demonstrating understanding of that process. So let's jump into the second example. This is a good one. So we've got y equals x take 2 times x plus 3 to the power of 3 plus 4. Okay. So in order to solve this, let's look at our process again. What does it say? Find the derivative and draw its sign diagram. That's our first step. So in order to differentiate this one, there's a couple of procedures we could follow. We could fully expand it, collect like terms and differentiate using simple differentiation. But that's a cubic factor. That's going to be quite annoying to expand that and then multiply that through. So could do it, but might take a bit long. So how else could we find the derivative of this? What have we got? We've got x take 2 times by x plus 3 to the power of 3. Product rule, excellent, okay? So we've got u is x take 2, v is x plus 3 to the 3. So in order to differentiate v, we need to use the chain rule here. It's going to be 3x plus 3 to the power of 2 times by 1. Alright, so I'll just leave that up there for a sec. And then you can see if you have any questions about that. We don't even need to consider the form, okay? Because when we differentiate that, like we're differentiating this term, disappears. Differentiating that term, that's that process there. Differentiating that, disappears. So we don't even need to consider it in the d1 and dx. So let's make our statement. U dash v plus u v dash. And I'm going to write it like this. Okay. So if we were asked to draw the sign diagram here, we could, again, refer to our calculator, but I'm going to try and just sort of do this all manually. So I'm going to make a bit of an argument here. What we want to try and do is write this in simplest terms. And when I'm looking at this, when I'm trying to simplify things, I'm always going, is there common factors? And you can see we've got x plus 3 to the power of 3 here, and x plus 3 squared here. So that means x plus 3 squared is common to both this term and this whole term. All right? So we're going to factorise x plus 3 squared. Okay. That's a tricky step. All right, or if you're a bit worried, just look, if you were to expand this, okay, with applying the distributive law, we're going to have x plus 3 to the power of 3, and then that's going to fit nicely in there. 3 times x plus 3 squared times x plus 2. So it's common to both terms. We pulled it out the front. Nothing dodgy happening. Then we're just going to collect like terms within here. So we're going to fully expand that and collect like terms. We're going to have x plus 3 plus 3x takes 6. 4x take 3. All right, and now we're ready to draw a sign diagram because it's something we can see the root straight. We're just going to apply the null factor law. If we're trying to find when this equals 0 in order to draw a sign diagram, we just need to go, well, when does x plus 3 squared equal 0? Or 4x take 3 equals 0. There are two solutions. And here we'll get x is minus 3, and that's a double solution. We know that because it's squared, it's a squared term, it's a double root. And 4x take 3 equals 0 is going to be 4x is 3, x is 3 on 4. So let's draw the sign diagram of dy and dx, the first derivative. We're going to have minus 3 and 3 on 4. They're the x-intercepts, and we need to go, when is it positive, when is it negative? So, from here, when we want to find out when it's positive and negative, I think there's three things we can do at the moment. Okay? So the first is we can graph the derivative function and go when is it positive, when is it negative. Okay? The second thing we can do is make a mathematical argument. So we go, what's a number between here and here? 0. Plug that into the derivative equation and see what its value is. Is it positive or negative? All right, so we can do that. The third thing we can do is we can remember something from year 11 maths. This is why we learn year 11 maths. So we remember with a quadratic, okay, so I might just write some quadratic, ax squared. If a is greater than 0, it's positive, it opens upwards. If a is less than 0, negative, it opens downwards. Okay, so we did that for quadratics. We also did that for cubics and for quartics. So if we have a cubic and a is greater than 0, it's going to follow this shape. If a is less than 0, it's the inverse, this shape. And for a quartic's easy to remember because it's just two quadratics, okay? So for a quartic, if we have a is positive, then we have two quadratics. And if a is negative, then we have two quadratics inverse. So we're looking here, like this, that's just some polynomial stuff, and you can explore that more and more, but obviously if you have ax to the 5, it's going to follow this one with another two roots, and it just follows those patterns indefinitely. So what are we up to? So we've got this as our derivative function here, and it's a cubic, okay, because we have a squared factor multiplied by a linear factor. If you're going to fully expand this, the highest degree is going to be x to the power of 3. And let's make a link there as well. Like, look, here you've got a linear factor times a cubic factor. So if we expand that, the highest degree is going to be x to the 4. And we know, like, if you differentiate x to the 4, you're going to get 4x to the power of 3. All right, so you derive a quartic, you get a cubic. You derive a cubic, you get a quadratic. So you can see all these links popping up. So anyway, we've got a cubic, and our value of a is positive. Okay, the number out the front here is positive 1. All right, so that means it's following this shape. All right, so it means it's going like this, up. It's going to touch there, all right, because that's a double root. It's not passing through that point. It's going down and then back up. All right, so that's what the derivative graph is going to look like. So if you're a little bit lost there, you don't have to apply that process. We can refer to our calculator or make a mathematical argument. And so what that means is it's negative, negative, positive. All right, it's below, touches. We know it's touching because it's double root, it's a squared factor. And it's going below and then it's passing through there again. We'll get rid of the graph there because we're only interested in the sign diagram. Okay, and then we've got everything we need to answer the question. Oh wait, no, we need the coordinates. And so we're going to go when x is minus 3, y is, and we need to put it into the original equation. All right, when x is minus 3, y is going to be all right. This is a nice one really. Because what's going on here, when we put minus 3, and that's going to be minus 5, but this factor here is going to be 0, because it's minus 3 plus 3. And so that whole thing is 0, and we're left with positive 4. So when x is minus 3, y is 4. So we've got the first coordinate of this stationary point, whatever variety it is. And then we've got when x is 3 or 4. This one's going to be a bit of a nightmare. Let's pull our calculators out here. And so, look, let me just explain again, like my thinking process when I'm doing this kind of problem, right? I'm not going to enter that into run. All right, that's like, it's going to take too long, and it's going to be ultimately useless in the end. Instead, what I'm going to do is I'm going to graph the original function, because that's going to be useful for me. It's going to be useful for me to check that I've got the answer right, and then I can just G-solve on the original function. So I'm just in my graph mode. I've got x plus 3 to the 3 plus 4. Set my V window to standard. And I want to know what is the y value. So I'm doing a y calc when x is 3 on 4, 0.75. Minus 61.917. Alright, so, and you'll see me doing this more and more and more as we're starting to deal with irrational numbers or numbers with more decimal places, is you'll see me writing 4 figures, alright, and then rounding it, okay, because it always says in the test and exam, 3 significant figures unless otherwise stated. So we state it to 4 and then round, alright, and that's just a habit I've got into. You can round your answer straight away if you want to, but that's good to demonstrate your rounding process. Okay, so that's the y value, and now we're ready to make our statement. So firstly, what is going on here? What kind of turning point is that? So we've got our table there in our booklet. We've got 4 types of turning points. All right, we've got local max, local min, and then we've got stationary point of inflection. And so that's what's going on here. It's a stationary point of inflection because the slope is negative and then negative again. So we have stationary inflection. At x is minus 3, y is 4, and we have, alright, so that's that coordinate there, stationary inflection. and then it's decreasing and increasing. Local min at x is 3 on 4, y is minus 61.2. And what an inflection point looks like on the graph, okay? So remember how you can have it's increasing and then decreasing, like that's a local max. So a point of inflection then, like this one here specifically, it's decreasing, it goes horizontal, and then it keeps decreasing again. All right, that's what it's going to look like on our graph. And so I've sketched the graph on my calculator. You guys won't be able to see it. I'm not going to waste time putting it up there, but it looks something like this. Okay, we've got our stationary point of inflection, so it goes down, goes horizontal, keeps going down, and then we have our local minimum. And we did that entirely manually, bar this calculation. All right, so we didn't even refer to our graph, but we can see the evidence on the graph as well. Okay, last one, sine x. So there's not so much maths involved here with this one. Okay, y equals sine x. Okay, step 1, find the derivative. dy and dx is cos x. You need to draw the sine diagram of cos x. Okay, and it goes on forever in both directions. So let's just constrain it from minus 2 pi to 2 pi. So let's say here's 0. And cos x is the one that goes like this. That's what the graph's going to look like. And so we're looking for the roots that are going to make it equal to 0. So if you have a look at your unit circle, we've got the derivative of sine x is cos x. We're going, what are the values when the x coordinate is 0? Okay, so remember cos is x. What are the values when x is 0? We've got pi on 2. We've got 3 pi on 2, etc. Okay, so it's going to keep going that way. And then back this way, it's just the inverse of that. It's going to be minus pi on 2 and minus 3 pi on 2. And I haven't drawn it to scale here. And it should be clear that that is not one of the roots. All right. When the angle is 0, the x value is 1. Okay, and then we need to indicate when is it above and when is it below. So in this region, okay, let me explain from our unit circle here. Remember, cos is the x coordinate. Okay, so here is minus pi on 2, isn't it? You're starting at 0, and if you go back pi on 2, that's minus pi on 2. Here's positive pi on 2, and in all of this region, the x values are positive. Okay, so that means between minus pi on 2 and pi on 2, the x values are positive. Alright, and then if you were to keep going in the positive direction, let's say you're going from there to there, and you're going to keep going this way, between pi on 2 and 3 pi on 2 is the next value in the positive direction. All in this region, all of the x values are negative, and they're positive. It's periodic, it's just going to keep repeating. And then the same here, we keep going back the other way, negative, positive, etc. So it's going to keep going like that forever. All right. So we have on this function, this is the main one we're talking about. We've got a local max at pi on 2 and a local min at 3 pi on 2 forever. So how are we going to answer that mathematically? First, we need the coordinates, of course, as well. So we're going to go when x is pi on 2, y is going to be sine of pi on 2. Which is positive 1. And when x is 3 pi on 2, alright, so like we can be really intuitive about that as well. Okay, here is the angle, x is pi on 2, what's the y value there? Positive 1, so unit circle has a radius of 1, so the coordinates of that point is x is 0, y is 1. And then down here, x is 0, y is minus 1. So you can get them there, you can get them from the unit circle. We've got the coordinates, we're ready to make an argument. We're going to say we have a local max, because we're going from increasing to decreasing at pi on 2. Let me write the answer up here and then I'll describe my reasoning. Okay, so if you were answering this problem, you would have just said local max pi on 2 and 1, local min 3 pi on 2 and minus 1. And you're absolutely correct if the domain is limited from 0 to 2 pi. Okay? If we read our question carefully, it says for all turning points on the function, every single turning point. So that means we need to come up with an answer that justifies every single case. So if you're going to keep going, so this is pi on 2, and if you're going to keep going around the unit circle, the next maximum point for the y value is pi on 2 plus a whole revolution. Okay, so hence plus 2 pi. Right? And then if you're going to keep going again, it would be plus 4 pi and plus 6 pi. And so this k2 pi, where k is an integer, remember z means any whole number, 1, 2, 3, 4. So it's just 1 times 2 pi, 2 times 2 pi, 3 times 3 pi. It's just continuous revolutions of the unit circle. And the same with our local min. All right, cool. So that is turning points. Let's get into it.